Good morning. I hope you're ready for this first session of the day. So, when I created this presentation, I wanted to give it a really good title. That's one of the most important things with a talk, right? You need to have a really good title. And I really like puns. So, I hope that by the end of the talk that you'll realize what the title was all about. So let's get started. A much better title, perhaps, a more clear title, would be the convergence of stream processing in microservice architecture. So how many of you are familiar with who I am? Just before we... Okay, perfect. Thank you. That's my Twitter handle if you want to make any nice comments, my email address, etc. So I'm here to talk about the convergence of stream processing in microservice architecture. And I believe that it will be the next logical and probably inevitable step in how we design systems tomorrow and forward. And I hope to be able to convince you that that is the case. So I have a bit of a distributed systems background, and I've also built some large-scale business software. Many of you might know that I've done the Scala futures work more lately. And of course, I work at Lightbend. And I hope, how many of you know who we are and what we do? Perfect. All right. Let's just dive into this. So, let's just have a brief overview on what we're going to talk about here today. We're going to do some time travel, which I think is pretty cool. Do you agree? Time travel is pretty cool? Yeah? So, we're going to have a look at some important events. Some past events and some current events and some possibly coming events and some possible even further beyond, like future events. So I think that it is becoming more and more clear that data is king. We're creating more and more data. We're creating data faster and faster than ever before. And we need to have tools and ways of working that deals with ever-increasing amounts of data. Do you agree? Yeah? So let's go through a bit of history on data processing. How many of you are familiar with what I call offline batch data processing? Processing files. Anybody processed files before? Like reading a file, transforming that file, and perhaps creating a new file, right? And the interesting thing here is that I will go through a bit of important sort of history data points here, but they will of course not be all of the data points. And the interesting thing here is that if you look at this, you'll see that basically all of the ways that we've been doing data processing in the past is still used today. And not only used, but we're actually creating new software that is using all of these different ways of processing data, which I think is interesting, because shouldn't we be moving, like using better and better tools? So what is the issue or issues with offline batch data processing? Any ideas, any suggestions? Anything? I will throw one out there. Latency. So we need to have the file before we can process the file. So there's a happens before relationship between receiving the full file and starting to process that file. But also, the latency accumulates, because if we have multiple steps of offline batch data processing, then the next step cannot start before the previous one has completed in full. So if we have many steps of processing files, then it tends to accumulate in latency. So by offline batch, we can not only think about files, but also perhaps reading and writing to a database. If we cannot start until we have all the data. How many of you are familiar with overnight batch processing? Yeah? It's pretty interesting today, especially when you're traveling and if you're in another country, a few time zones away, and you can't access stuff that you would normally be able to access because they're currently running some batch job and the data is not there. But also, I mean, it's not only databases, but also how we write those transformations. How many of you are familiar with bash scripts or doing work in a term? Isn't it sort of weird? How many of you are version controlling your bash scripts? How many are not version controlling your bash scripts? Right? They're still data processing. They're still parts of a system, but somehow it doesn't seem like they have all the same tooling that we normally use when we do data processing. But also, it's pretty hard to scale out offline batch processing. It's typically a script, and how do you run that script on multiple machines, and who runs it, and when, and how do you coordinate? That's sort of left up to the programmer. But also, what happens if you have 1 gigabyte of a file of payments or some other really important data, and the job fails somewhere halfway into the data processing, or even at the very end? Can you rerun that batch? Do you know why it failed? So the next step is MapReduce. So how do we take these things and how do we process them on many machines, but it's still sort of file to file. We're reading files and we're writing files and then we're reading files again and then we're writing files again. We can now parallelize the actual processing, but we still cannot really start until we have all the data. But what does it mean to have all the data? What is all the data? How do you know that you have all the data? So, how do we deal with data as it flows? Or how do we deal with data as it arrives? It's unclear in some cases. What if data arrives late? What if we are supposed to process everything that happened within a day and then some data comes in late? How do we know that we have all the data? One way of trying to deal with processing data as it arrives was called the Lambda architecture. And that's essentially having that sort of MapReduce style batch processing pipeline, but also having an adjacent stream processing pipeline that can process data as it arrives and perhaps create some sort of good enough approximation of what the end result will be once the batch processing has processed that data. So it gives us some of the ability to know what the current, for some definition of current state is. But what is the problem with this? Well, if we need to have 2 completely separate systems, then we also need to maintain 2 completely separate systems. And if they are different enough so that they run on different infrastructure, now we not only need to maintain the programs, but we also need to maintain the infrastructure twice. That's not necessarily super convenient. How do you deal with failure? What if the batch processing fails, or what if the stream processing fails? So how can we get away from the batch processing side of things? Well, one idea was to make the batches smaller. We just make the batches really small, but they're still batches. And it means that the latency window is much smaller. But there's still a window, right? But what was good also that something like Apache Spark made it possible to do this in memory, so that we didn't have to go disk to disk or file to file. So that's an improvement, right? But there's still benefit of having durability, storing the results. Because if something fails, you don't necessarily want to recompute everything. So you still need to have some form of durability, some form of storage. But we're still not doing like live data processing as long as we're doing batches. If we have data, but we cannot process it until we have more data, then clearly we're not processing it live. Services. Anybody has here ever written something which would qualify as a type of service? Yeah? Cool, cool. It's interesting that there has been quite a few kinds of different types of services. So, client server, by client server I mean when you have software where the client and server is co-developed. They are specialized. Anybody ever worked with a system where the client and the server was really heavily coupled so that you couldn't necessarily just upgrade the client without upgrading the server, and then it wasn't clear whether it was possible to upgrade the client at this time, and then you would sort of hard to figure things out. And you also need to solve some pretty difficult problems for every single client-server pair. Do they have some specific protocols that they deal with, or do they have failure guarantees or semantical guarantees that you need to encode in the protocol, or do you encode it in the application? It's not necessarily clear. And you also need to do it on your own. But also, when you create your own network protocols, how do you know that they're going to be traveling smooth across the network? Is that, if perhaps you're using UDP, do you know whether it's going to work well over the internet or over the corporate network infrastructure? We don't know. Perhaps some protocols are not allowed at all. Perhaps they're down prioritized. Don't know. But then we had Corba and Microsoft DCOM. Now we can use an intermediate description. We can create a sort of a schema first, and we can generate clients and servers from this description. So now we're not super coupled in terms of how we develop these things, but there's a meta description of the service. Clearly that is an improvement in this case. But are we using this today? And why are we not using this today? Well, one of the major issues is that when you try to treat something as if it is local, when it is remote, and you don't necessarily see, then how do you know what the semantics are? If I call this method, what happens? Will it block? For how long will it block? Can I provide some sort of timeout? What happens if I couldn't connect to that thing over there? Or what if that thing couldn't connect back and send the response? It's sort of the fallacies of networks. Everything could happen. You could have multiple responses, packets being redelivered. So the programming model where you have something that looks as if it is local, but it is remote, creates the wrong kind of expectations, and it's really hard to see what's going on in the program. Anybody familiar with this? Anybody ever done any sort of 3-tier architecture? It was typically 3, right? It was never N. Really, it was typically 3. It was mostly 3. And for those of you who wasn't really exposed to this, The idea was to decouple the system such that the persistence layer would be separated from the application level layer, which was separated from the presentation layer. So that means that everything needs to possibly traverse 3 distinct layers for every single thing. But you still have most of the problems that you had with Corba and DCOM. What if something is remote and it looks like it's local and you're assuming that it is local? What happens? And also the latency. What is the latency? You never know. And if you cannot specify those timeouts, for how long will you wait? Also, what happens when you do wait is that when that system on the level below becomes overloaded, then everything above starts waiting even longer. And then when you've saturated the layer above, then everything above that takes longer and longer. So you're sort of locking everything in place. That's not necessarily a super awesome behavior under load. Anybody familiar with service-oriented architecture or enterprise service buses? So, SOAP, web services, WS star, XML. What happened? Well, we still had these sort of single points of failure and the single points of contention. And whoever ever at any point encountered a service that didn't really match its published contract? Like you would get the description and you would, nice. And then you would try to call it, but it wouldn't necessarily agree with its contract. That happened pretty soon. And integrating through a single location, like going through a single location to integrate with other things, just creates this one single piece of contention, which under load will possibly bring everything down. That's not necessarily awesome either. All right, what's the next step? Anybody ever written anything that would go under this definition? Like something that uses HTTP or REST for some definition of REST? The interesting part, I put HTTP API first because I think that's what 99.5 to 99s actually do, because the REST part is really hard to get right. But what was awesome with HTTP was that it was really good at traversing networks. There was infrastructure for this. There was proxying and caching. But there were just so many things that you could do. Just so many things. Do you use content negotiation? Do you use your own headers? Should you be using some other headers? Are you always returning a 200 response? Or are you using some specific error codes? It was extremely flexible. It is extremely flexible to use HTTP to create services. But that also means that it's really hard for people to do the same thing, to use the same approaches. But also HTTP, it's at least in the 1x era of the protocol, was rather blocking, head-of-line blocking, and you couldn't necessarily respond until you had consumed the entire request. So there was a bit of inherent latency in the protocol. So that's why HTTP2 was created, and fortunately that solves some of those issues. So less head-of-line blocking, don't necessarily need to pipeline and just consume one at a time, but you have multiple lanes. So this is a short, compressed history of data processing and services. So what do we have today? What do we have on this topic today? Any guesses or any suggestions? Streams? Streams? We have live stream processing, and there's a footnote there because if you use the word real time, then everybody has their own definition of real time. Live stream processing, we do have tooling today to consume and process data as it arrives. So that's super cool. But we also have something which is microservice architecture. So we have two distinct ways of writing code or building systems. So we have pure streaming and microservices. And on the microservice side, we have things like gRPC, streaming RPC. Not necessarily the blocking RPC kind, but really being able to send a request and have something which corresponds to the response when it gets there. So that's an improvement. We don't need to block anymore. That's great. But we also can stream input and output, which is really good if we want to be able to stream input and output. Because imagine that you need to be able to send a 1 gigabyte request. You wouldn't necessarily want to load that gigabyte into memory on the server as it receives it, because that would not be extremely great. But what is great about services? What do services do that data processing doesn't necessarily do? Access control, encryption, authentication, validation. And we can receive data and information from the outside of the system. And that's good, right? We can get data into our system, but we can also get data out of our system. We can have services that respond to views or projections or being able to control the environment or control the domain. They're really good at providing the domain, the business domain aspect, modeling the domain. But what is the stream processing good at? Cleaning up data, enriching the data, adding data to the data, transforming the data, aggregating the data, doing analytics on the data, machine learning or what have you. But it can also create views. We can do aggregation in terms of providing some sort of view to a system. So they have some different but good qualities. But what's interesting is that they also have some shared requirements. Because when you have live stream processing, when you need to be able to process data as it arrives, that is the same for both services and stream processing. It needs to be available. If it's not available, it doesn't matter. So it needs to be available, both of them. That was not necessarily the case when we were talking about batch processing, because you could receive the entire file and it didn't really matter if the thing that processes the file is available when you receive the data. We also need to be able to elastically scale this thing. We need to be able to cope with higher loads, and sometimes, and oftentimes, load is not evenly distributed. Not even in the sense of files, because in the sense of files, you get the file, you don't get the file all the time. So there are spikes in the load, and you need to be able to deal with that. But we also need to be able to deal with failure, both in the terms of microservices and in the terms of stream processing. There will be data that is malformed. There will be requests that don't really make sense. There will be infrastructure failures. There will be human failures. There will be all kinds of failures. And they both need to be able to be upgradable. We need to be able to deploy parts of the system separately. We need to be able to fix bugs in one place and not have to roll out over the entire architecture or the entire infrastructure. Because we want things to be available, and it can't be available if we bring everything down to put up something new. So it's interesting to see that both of them have the same shared requirements. But we also have, as we do live stream processing, we have service level objectives. We need to be able to respond within a certain amount of time. We need to be able to process data within a certain amount of time. Because some data is worth most when it's the newest or the freshest. And you probably suspect where this is leading, right? There is already a formalized architecture for dealing with these things at the system level. So we can achieve availability under failure through resilience and under load through elasticity. And the key driver is being message driven, being able to communicate using message passing. And I think we also need to lift the level of which we view things from the component level to the system level. Because no matter if we just create a component that transforms A to B's, it still matters how it fits into the bigger picture. Who will rely on these B's to be produced, and who will produce those A's? So by lifting the perspective, we can manage how the components interact. And when components interact and when you create systems, and it's interesting because there is no such thing as a non-complex system. The entire definition of a system is that it is complex. So we need to be able to deal with these systems. And we need to have ways of reasoning about the systems, how they behave, under load and under failure. And I think that means that we need to embrace thinking about distributed systems. The interesting aspect of being message-driven is that now it doesn't necessarily matter where something physically lives anymore. If we can address it, then it can be locally on the machine or it can be on some other machine. We can hold a message waiting for something to come back online. So there's decoupling, both in space and in time. In space, as in it could live on this machine or that machine, and in time, as in that thing over there doesn't necessarily need to be available at the same time for some definition of same. When we have components that communicate, since they live at different points in space and at different point in time, we need to be able to deal with if this component produces data faster than that component can consume data. And it's not necessarily a static thing. It's easy to think that this is a slow component and this is a fast component, but that's not necessarily reality. A component could be slow at this point in time because the machine is currently overloaded, or the GC is currently running. So over time, it's not about statically allocating different amounts of resources, but it's also being able to say, I can't deal with this data at this point in time, so you'll have to wait. And what's interesting about being able to say that is that now you're moving the knowledge that there is no current capacity to the utmost producer of the information. Because through a system, if you have a sequence of steps and the end step is too slow to keep up, then it tells the upstream that it can't deal with it. Then the upstream will have to make a decision, like, can I cache stuff? Can I compress the data? Can I throw data away? And perhaps it can't make that decision, so it can say to its upstream that I'm currently not able to receive any data. And since that information travels upstream in this process, it will at some point reach a place that has the most knowledge about the data, which is the producer of the data. And the producer of the data tends to be the thing that can actually know best on what to deal with the data if it cannot send it. So for instance, in the sense of a sensor that senses temperature, perhaps it can store it locally, perhaps it can produce some latest reading, or perhaps it keeps some sort of histogram over the distribution of temperatures that it has seen over the past X amount of time. Because we don't necessarily want to just discard data. We want to be able to make that decision whether we can and should. And what's important here is that we cannot have the components block each other. They need to be able to be autonomous. So if a component cannot send data, it should still be able to do other things. So what's cool about reactive streams is that it's in Java 9. And what's also cool is that once you have a mechanism for communicating flow control, then you can integrate with other protocols that have flow control. So for instance, you can integrate with TCP flow control and have the flow control cross machines. So if that is today, we have microservice architecture and we have stream processing. What can we do with that? We have stateless stream processing, where we just transform A's to B's, for instance. And we have stateful stream processing, where we keep information from the previous events or the previous data that we've processed, so that we can influence decisions and data on the next steps. But we also have different kinds of microservices. We have both the RPC style, where you have requests and responses, which is really good, right? We're able to send commands and get responses back. But we also have what's currently called evented microservices. And an evented microservice is a service that takes events as inputs and produces events as outputs. So it's a reaction of sorts. But we also have the actual events. Remember when I said data is king? We need to be able to, it's not just data, right? It is not about the data, it's about the information. It's not just the binary, the ones and zeros, but it's what it represents. And I think when you have an evented microservice, the API is the event. The API is the data. So if the API is the data, then we need to be able to describe the API, right? How else would we be able to call it or use it? So that means that being able to describe the data becomes extremely important. We need to be able to reason about what the data is or what it means. So let's just define what we mean by events. To me, an event is an immutable recording of an observation. Let's think about that for a moment. It's a recording, so it means that we can transmit it. It's immutable in the sense that we don't want it to change under our feet. But it's also, and most importantly, an observation. Something somewhere has made an observation, or, in another word, a conclusion about something. We can disregard external observations, but if we accept them, then we can't necessarily just retract them and pretend that we didn't see them. We can invalidate those observations, but we typically don't want to delete them in the physical sense of deletion. It might be necessary for legal or moral reasons to delete, but we typically want to keep as much information as possible. And the reason why you typically want to keep as much information around as possible is that it's so much harder to reconstruct information than it is to keep it. How many of you have ever written code that tries to recompute or recreate information that was thrown away at some point? That's not necessarily super fun, and you might not always be sure that you got it right. So if we can keep the information for as long as possible, then that would be a good thing. So if you want to read more about the definition of events and stuff like that, there's a link to a speaker deck that is really good on that topic. Most importantly, knowledge at every single component that receives observations accrues with every single received event. So we have more and more information available at every single point. So why are all events created the same or of equal importance? I think that there is a distinction to be made between external events and what I'm going to talk about next, which is internal events. Observations that are transmitted to us, what do we know about them? Could they be, perhaps they're not correct? What do we know about the sensor that created this event? Is that sensor 100% calibrated and has zero margin of error? Perhaps that it degrades over time. So events that were created externally and submitted to a component is slightly different from events that was created internally by the component. So imagine, for instance, that you have a component that receives payments. Perhaps let's call it the fraud detector. It receives payments from the outside, and at some point it might emit events, let's call them suspected frauds. But the thing is that in order to suspect a fraud, you might have to look at multiple payments, right? It might be a pattern or a sequence that doesn't really make sense, that looks weird. So it might need to keep some internal state, right? It needs to remember where it is in its current sort of suspicion level for specific sequences of payments. And it might want to record that internally. Like here, I suspected this, but it's not necessarily a strong suspicion. So unless there's something that happens within X amount of time, it doesn't really matter. It's just I had a bit of a hunch, but it might not be a problem. But the interesting thing here is that if we have internal events, we can decide whether we want to expose those internal events as is, or whether we want to convert them to other external events. External that we can transmit to others. So that means that there is a clear boundary between where we can do things like event sourcing. So the component can store and retrieve events that it created itself, and it can have external events that it receives and external events that it produces. So there's a decoupling between the internals of the component and the externals of the component. Does that make sense? So, and Miles will think here, Victor, did you invent this notation yourself? Yada, yada. I will unpack this quickly. For some evented services, you can think of it as you have some behavior and you have some current state, and you apply the current state and a new event to this behavior, and that yields a new behavior and some effects that will then produce a sequence of other events and a new state. And the reason why that is an effect is because you might want to store those events. You might want to store things as a part of processing that event. So service takes in an event, might be producing events as a result of that. But how do you reply to an event? What does that even mean? Should you reply to an event? There is no semantics like that, right? So, well, what if evented services are just stream processing stages? It just takes data in, does some transformation, might store data locally, might have memory. So it's a possibly stateful stream processing stage. So evented microservices could be stream processing stages. So that's why I think we might be looking at a convergence between these different models. Because they're sort of starting to look rather the same. So is this just the solution? Like we have, we take, let's say that we have an RPC service and we have an evented service and we lift that just into the stream processing pipeline and then we're done. What? No. We need to be able to respond to things as well, right? We need to be able to receive things and respond to things. We can't just unify evented services and stream processing. We need to unify more. So an RPC service, something that receives a request or a command and produces some sort of response, could be just a behavior with some current state, and you apply a command to that, and you get a new behavior and some effects that will produce the next state, and send a response with that effect as well. Interesting. Sort of looks like some other model of computation, perhaps. Something like an actor or something. So an improved solution here, let's say, what if we just lift the RPC service into a stream stage, and as a part of lifting it, we take events and repackage them as commands, either by lifting them into a command or converting it to a command. And then we submit that command to that service. And then we just capture the response from that service and repackage that as an event. Well, what if we could just derive microservices from data streams? Interesting. Could we do that? Could we derive microservices from data streams? Well, for instance, look at ingestion. Typically in a system, you want to be able to receive data from the outside. So you might have some services that will represent those endpoints that will receive the data. Well, what do we need? What if we were to derive a microservice for ingestion? What would we need? Well, we would need some sort of schema for the events and some sort of codec so that we can receive and create the events. We need some form of authentication and authorization so that the service doesn't get data from anywhere. And we need some sort of transports, might be gRPC, might be HTTP or something, and a destination for where that data should go. And given those pieces, we should be able to generate an ingestion microservice that takes requests that contain events and produces those events inside the system. But we could also do the opposite. We could generate or derive services for views, for projections. Because if we have that schema, we have the authentication and authorization, we have the transports, we have some sort of source of information or an aggregate that we want to project, then we could just generate a microservice that projects that. But we could make even complex projections, even more complex. Because given a upsert or an aggregation function, and given n number of selects or equivalents or views, we could generate aggregators and we could generate projectors from that take those queries or views and run those on a store that stores the data and projects that data out. So the unification of this can now give us best of both worlds, right? We have both microservices that is good for request response and being able to have components and well-defined boundaries. And we can expose a stream processing pipeline as microservices. And we can also independently upgrade parts of the pipeline. We can have stream processing followed by some microservices, followed by some stream processing, and followed by some microservices. So how do we develop these things? How do we develop these converged applications? Well, definitely we're going to need some sort of deployment orchestration. We need to be able to deploy and upgrade the different pieces of the system. And we need to start thinking about events as APIs and thinking about events first. And there are some strategies for dealing with how you come up with what events make sense for your domain. So you can have a look at that. But we can also do some metadata-driven continuous deployment. What if we know how we deploy things? So we just have something new and we know where it should be deployed. But most importantly, we can use the right tools for each component. If something makes more sense as a stream processing part, then use stream processing for it. If something makes more sense as a microservice, then use a microservice for it. So how does this relate to sort of serverless or functions as a service? I think from a functions as a service point of view, it's not necessarily just about having functions. It's about having components. So it's about being able to be stateful. I think that is really important. And you also need to be able to think about the communication in the system. We need to be able to orchestrate how these different things fit together. But more importantly, how does this relate to Scala? You're like, how does this relate to Scala at all? Well, the interesting thing is that Scala has proven to be extremely useful for both stream processing and creating microservices. I don't necessarily know any other language or platform that is this suited for both these things. But also, I think creating systems as pipelines is the future. And we're working on some of these things at Lightbend, being able to do these things, running these sort of hybrid systems. Doing data processing where it makes sense, or stream processing where it makes sense, and doing microservices where it makes sense. So there are some cool news coming there. But what is beyond this? Is there even something beyond this? So I'm typically not super good at looking into the future. It's not one of my stronger points. But what I think is, if you extrapolate here, what could be the future? I think we need to start embracing the edges of the system as a part of the system. Because fundamentally, anything that communicates with a system is a part of that system. And we can move so much more logic to the edges. If we can do stream processing and services on the edges, on the devices, then we don't necessarily need to have this sort of centralized infrastructure. We can do machine learning on devices. We can do stream processing on devices. We can do services on devices. And I personally think that some things like the actor model is perfect for this. But that also could lead to what would be true serverless. Perhaps at some point we don't even need the servers anymore. There is only the edge. I don't know. You tell me. So this is all I had for you today. I hope that this has been interesting to you. It definitely is to me. If you want to explore some of the stuff that we're doing, here are some links. And thank you so much for attending this, and I'm really happy to be here to talk to you today. So I'll be around. For most of the day, so if you want to chat about anything, just grab me in the hallway and we'll talk. Thank you.
Thank you so much, Viktor.